meeting when we had this. This is recorded, by the way. Joshua brought to my attention that if you're going to get the x prime and the y prime values out of the intersection of the EOL, the enriching section operating line and the feed line, the intersection will not be right on the curve. Actually, it's below the curve because that's how it's supposed to be. That way we can create the stair-like line or the stepwise procedure of determining the theoretical number of stages. So I told Joshua that before, that's the procedure that I'm giving the student. That way we won't have any problem having to look for the equation of the curve. Even if we are provided with the equation of the curve, it will be a curve, and that will be giving us two sets of values for the x and the y, because if it's a curve, it's either the least degree of the equation is second degree, or it could even be third degree. In our case, since the curve is parabolic, it would more or less be second degree. So I mentioned to Joshua that that's just the very crude way of us finding the x prime and y prime. That way you can find the R minimum. I hope you still remember what you studied, that in order for you to find the minimum reflux ratio, there's a need for you to find the x prime and the y prime. And that's how I gave you the instruction, and that's how you should find the x prime and the y prime from the intersection of the EOL and the Q line. Now, I have edited the slides that were posted in Canvas already regarding how will you address the very crude value of the theoretical number of stages analytically determined using that particular method. Actually, if you have already read the sample problem that I gave you to read in Genku Place, and you've read forward and even in McCabe, there is a procedure in determining the N minimum without having to find the R minimum. So what I mean is you'd rather find the N minimum first. That way you can find the R minimum if that is the case. And what you should do is actually also outlined in Jan Kuplis, both in Jan Kuplis in McCabe. The thing with this procedure class, where I don't really discuss this in class, is it's a trial and error process. So the formula that I have read is found in Jan Kuplis, but it has an equivalent in McCabe. So it has an equivalent formula in McCabe, also having the summation here and also having the theta. Okay, now you solve for the theta in this particular equation using the trial and error. That's one way of finding the R minimum. So you find that you are already given the Q and you determine the theta from this particular formula. I will give you the instruction, or I will give you the procedure on how you find the theta out of this particular step. But the thing, class, is this one is trial and error. Let's say, for example, you know already and you already determined theta out of this. Of course, you need to know the Q. You need to solve for the R minimum using the theta that you got from step 1. So meaning, let's say, for example, you have a 1.2 value for theta here, you will solve for R minimum from this particular formula. They come in pair in Jan Kuplis. The same thing with the equivalent in McCabe. So the theta from step 1 is substituted here to get the R minimum. So if you know already the R minimum, then you have only to go back to the graph this graph that we have. So you have R minimum already, then you will have the NM and N ratio. So after that, by the way, before you go to step 3, then there's this note that you have to take note of. So how do you solve for alpha? And this is the relative volatility that you see here, alpha sub I times X sub IF. I means or represents the components that are present in your feed. In our case, since we only have 2 component feeds, I don't give 3 component feeds because that would even make things complex. So let's say, for example, you have a 2 component feed mixture. One is said to be the low boiling point component and the high boiling point component. So the reason why you have the summation symbol here, it's because you will have 2 products in the numerator, meaning you will have two terms in the numerator consisting of the products of two terms. What are the products that we're talking about in here? The relative volatility of the low boiling point component times its small fraction in the feed plus the relative volatility of the high boiling component times its small fraction in the feed. So you have two terms, meaning you have two fractions, because the denominator that you will have here will depend or will copy simply the alpha that you have in the numerator. I will show it to you later in the form of the whiteboard. That way it's clear for you. Anyway, the manner of determining alpha in here is trial and error. So as to how long will you get the alpha, it really depends on your skill on how you substitute the value of alpha here. That way, what you have on the right side of this equation in terms of the value will be equivalent to what you have on the left. The theta that you have here will be substituted in this equation, which is also a summation. But this time, it's not anymore a trial and error because you know already the theta in here. Now, in here, in the numerator, you also have the alpha and the xt, but this time, it's already the distillate that we're talking about. Since your feed is consisting of two components, it follows that your distillate will also have two components, the low boiling point and the high boiling point component in the distillate, and you will multiply their corresponding mole fractions to their relative volatilities. In the two formula class, if the relative volatilities are not given in the problem, you are the one who's going to determine these relative volatilities. How? So based on our discussion in the previous meetings, I guess 2 weeks ago, in terms of relative volatility, that would be the pure vapor pressure of A with respect to the pure vapor pressure of B. In the case of this one. So if it's the high boiling point component, that would be pure vapor pressure of the high boiling point component over the pure vapor pressure of the low boiling point component. That's how you get the alpha if it's not given in the problem. What would be the basis in determining the alpha, the relative volatility, if it's not given in the problem? The basis would be the temperature that is provided, the temperature of the feed or the temperature of the distillate in that case. If you're not, again, provided with the temperature of the feed and the temperature of the distillate, you should have the temperature equilibrium diagram or the boiling point equilibrium diagram equivalent to the one that I have shown you, which has the saturated liquid and the saturated vapor curve all in one particular diagram. So using the mole fraction of the low boiling point component, you'll be able to find the boiling point of the feed and the boiling point of the distillate because you have the mole fraction of these two. Once you already have the temperature of the two, then that would be the temperature that you're going to use to find the relative volatilities. So the thing with this particular method of trial and error, finding the RM, it's really very tedious, especially if the alpha is not given. And if you're already given with the alpha, the thing is you have to find theta using trial and error. Now, there is a sample problem in John Copley's and in McCabe that solves for theta, but it's already involving multi-component distillation, meaning it's not just a two-component distillation, but rather three or more component distillation. But the process of finding the theta, whether you have a two-component feed or a three-component feed, it's just the same because you're going to do it tabular. So that's your step one. This is your step two. So how are you going to solve for alpha? It's already in here. Okay, based on the average temperature of the top and bottom of the tower, or you can simply base it on the temperature of the feed. This is an option, or you base it on the temperature of the distillate at the top of the tower, or you can use the alpha from Finsky's equation. initial class, ang A, B, C that I place here on the note of finding the alpha are your options. It's not that you're going to use all three. So if you want to find alpha using this one, then you can use this particular procedure. You get the temperature of the top and the bottom of the tower based on the mole fractions and average it. Then you get the pure vapor pressures. Of course, after the pure vapor pressures, you will be able to get the relative volatility. That's for letter A. If you're going to use the procedure, this procedure in finding alpha. If you don't want this, you can use the procedure that is outlined using Finsky's equation. The sample problem is already in this slide. You follow the procedure in finding alpha for that. Or the very simple way, but again, it's more crude compared to the first two, is you just simply base the temperature that you're going to use for finding the pure vapor pressure on the feed temperature. Iya lang gid ang feed temperature. You don't need to find the temperature of the top and the bottom of the tower based on the mole fraction of the bottom's liquid and the distillate. So any of these three, according to John Kuplis, you can use in finding the alpha that you will need here in the formula. Same thing with the alpha that appears here. Now, after you're done that, you find graphically the x prime and the y prime, which may depend on the availability of the equilibrium data or the graph. Okay, so you get the x prime and the y prime. That way you can find the R minimum. You can use that. Or you can use this one, which is very crude. But I think the easiest way of finding the number of stages in this case is the use of the Finsky's equation, which is already part of sample problem number one, the only sample problem that is going with this set of slides. There you can find the procedure in finding the minimum number of stages using Finsky's equation. If that is a case, then you can find already your theoretical number of stages. But the thing class is, if we will consider this very crude and we would like to get the more accurate way of determining the number of stages, this is how we do it. Even if you read McCabe or even if you read Jan Kuplis, this is really the procedure of finding it without having to rely on this particular uh, option. This is just an option. It's a crude option of finding x prime and y prime. That way you will have the R minimum. And that's it, class. So far, do you have any question as to the steps that we have here before? I'll show you how you go about finding this one, or how is this particular equation to be done when you are the one who is answering a problem and you need to find the theta and what would be the value of alpha and x that you will substitute here, since you have here a summation. Do you have any question? Actually, the first two in here, they come in pair. Duha gini sila pares para makuha mo lang ang R minimum. Kung makuha mo na si R minimum, then you go to the graph, you still need to get the N minimum. That way, you'll get the theoretical number of stages. To get the N minimum, then you use the Finsky's equation. That's it. Or, if you don't want to use this one, then amo ni. But the thing is, I haven't encountered a problem. I said I'm going to give a sample problem. I haven't encountered a problem wherein the equilibrium curve is provided with an equation, or the problem is providing us an equation for the equilibrium curve or the line. Wala pagid ko sa may nasumala nga problem nga amo na. So more or less this one cannot be used anymore. But just in case it would be given, then you can use that. This one is very crude, as I've said. Now, I'd like to go to the whiteboard and show to you how to solve for the theta using the formula that you have there. For example, in the case of the first formula, you have 1 minus q being equal to the summation of alpha I I think we have the feed in here. In this case, we have alpha I minus theta. Now, if I will specifically write that one, um, disregard this class. If I will have this for a two-component mixture, then I will have alpha x. I will just have a subscript here of low boiling point component over alpha minus theta. This one means that you're going to get the product of the alpha and the mole fraction of the low boiling point component in the feed. So this is for the feed. So we'll have another fraction here which constitute of alpha and XF, but this time for the high boiling point component divided by the alpha minus theta. The alpha that you have here for the low boiling point component, it should also be the same that should appear here in the denominator. If this is the alpha for the high boiling point component, then this would be in terms of the high boiling point component. How do we determine the alpha based on the low boiling point component and the high boiling point component? So let's say for example, this would be the pure vapor pressure of the low boiling point component over the pure vapor pressure of the high boiling point component. If it's the other way around, if it's the alpha of the high boiling point component, that would be the pure vapor pressure of the high boiling point component over the low boiling point component. So the reciprocal, they are reciprocal of each other. This is based upon, now based on the options that's provided there, this is based upon the T average. This could be based on the T average of the what? Bottom and the top of the tower. So getting this, as I have mentioned a while ago, you need the temperature boiling point diagram, equilibrium diagram for that, the one that has the saturated liquid and saturated vapor curve in one graph. So if it's not given to you, then you cannot use this particular procedure anymore, unless otherwise the problem gives you already the temperature. This is one option, you get the T average. Another option, I'll put here an or, is based on the temperature of the feed. You simply base it on the temperature of the feed. Same thing in here. So you also base this on the T average. Anyway, if you have this one is just the reciprocal of this, the one that I have written on top. Or at the boiling point temperature of the feed. The thing with this class, that the temperature, the thing with these temperatures in here, you need that boiling point equilibrium diagram for you to be able to get these temperatures in here. Unless the problem again gives it to you. So it has to be well written, specified in the problem. If it's not, most of the time, class, the feed temperature is given. That is why John Kuplis gave us an option. Kung wala, ginhatag ang boiling point equilibrium diagram for your system, especially if it's not benzene and toluene, then they are not readily available. Then use this one. Amo naman lang ginimagamit nyo ang temperatures ng feed as a basis in determining this. You get this in section 2 of your handbook, the pure vapor pressures of the low boiling point component and the high boiling point component. This is an option of finding the alpha. Or another option is finding the alpha using the Finsky's method that is explained in the sample problem I also placed in this slide. Ari man di sa slide ang pag-determine ng alpha using Finsky's equation, or you could use that one. So you have three options in finding the alpha. Either based here, or based on Finsky's equation, which does not need the temperature. Hindi kinahanglan sa Finsky's equation and temperature. All it needs is just the mole fraction of the components in your mixture. But nonetheless, class, even if, for example, you know already the Q, You already determined the Q with these two terms here on the right, and your goal is to find the theta. It's a trial and error thing. You have to make sure that what you have here on the right side is comparable to the value that you have on the left. Okay, once you already have this theta, you go to the second step that is given in the slide. So I'll go back to the slide again. This is the second step. So the theta that you got here, you will use again in finding the R minimum for you to be able to use the graph. The graph that is found in your handbook or the graph that you have in John Please. By the way, it has also an equivalent in McCabe. So the trial and error is in here, but in here you already can find the RM. Even if you already have the RM, the R sub M or the uh, minimum reflux ratio, you still need to find, based on the graph, you still need to find this one, the N minimum, because what you'll be getting here is just the ratio of the N minimum and the N. For that, you have to use Finsky's equation. If you don't want to go through this, you can have this one. You can have this very crude estimation, but if I were you, I will divide it. Probably you will need to divide it by zero point 0.8 or zero point 0.9. That way, what you will be reporting as your answer is more or less close to the theoretical number of stages if you will do it graphically. Kaya ini siya crude gini siya. That's the one that was pointed out by Joshua last meeting. Although my students then before did not raise any concern as to why use this one, wherein this one is very crude, because probably they already read that you will have to go to trial and error in this portion if you will not settle for this one. After assigning the sample problems to read, they would rather go through this. Anyways, if you will be provided with choices as to theoretical number of stages, they will not be choices that are very near each other. So they will be far from each other. That way you can really select the one that is probably the nearest to the uh, final answer or the correct answer. The reason why that before when I discuss, I a lot of time in the graphical approach, because even though it's graphical, it's very procedural. The students can understand easily and follow through the procedure. When we do analytical with the use of the graph, this is where the students get stuck up in the trial and error way of finding the data. If you have any concerns now as to what I have just discussed, you can raise those concerns before I go to liquid-liquid extraction. Specifically, Joshua may have some inquiries, or for some of you who were present last meeting, regarding, because when you have your quiz on Thursday, you will do it with the use of this graph. You will do it like this. Although I will specify the procedure that you will use, that way we will have a uniform procedure to follow. What I'm just trying to drive out here is that you will know how to use this one, and you will know how to use the property tables that are found in your handbook. So I will just outline one specific procedure. What do I mean with that? Hindi man pwede nga si student A maamuni, si student B maamuni, si student C maamuni. Kaya ayawan ko na karon solve. Then I will have to prepare 3 different solutions for that. So I will specify what particular procedure, or the, shall I say, the simplified way of doing things. That way I can simply see that you know how to follow steps, because what we're doing here is just following steps or procedure. And where are you going to get the properties, the information that you will substitute to the formulas that were provided to you. So if you have any question now, you may raise them before I go to the next topic. Any question regarding this, you can complement what I'm discussing here with readings in both John Couples and McCabe because you can find it there. This particular formula and its equivalent in McCabe. Any questions so far? Let me see. Oh, see, you're only 22. I don't know where the others again. Let me see. Is Joshua here? Joshua.
Hello, miss.
Okay, so do you see this one, Joshua?
Miss,
Did,
nakita ko na miss sa Paris, miss.
so na-follow mo man?
And hindi ko galing gets bala miss kayo nang nagamit ko bala. Hindi pwede na siya miss nga ang average relative volatility na lang miss nga nakuha sa Fensky equation bala miss.
Mm-mm.
Amo nang gamiton namon sa AI bala miss or
Sa
hindi.
tanan-tanan?
Oo,
Meaning,
miss.
even if we talk about the low boiling point component,
Hindi miss.
ano man?
Kay nabasa ko man bala miss nga kung ang low boiling component tupuan na miss ang iyang relative volatility miss. Kay
Automatic, kay gina-assume yun na nga 1 na lang.
kay it's relative, di ba miss?
Oo,
Relative sa isa.
oo.
So which means ang first na lang gid miss ang high boiling na lang gid miss nga volatility. Di do ka nabasa ko miss nga mag-solve bala miss ang n mean bala miss.
Mm-mm.
Di gaka-solve naman natin ang average relative
Mm-mm.
volatility
Mm-mm.
bala miss ang square root of
Mm-mm.
ALD. Pero hindi ko sure kung sakto na miss.
Mm-mm. Oo, before ka kaka-solve sang imo n-mean, maagi kagidaanay kay hindi siya ma-solve ang n-mean without the alpha. Mm-mm. So you mean that alpha that you use in determining n minimum, amo na lang na ding alpha nga gamiton mo
Oo,
para
miss.
hindi labot
Hindi ko sure
kay
miss kung pwede na miss. Hindi ko sure kung pwede. Pero
kay gina-approximate naman na gani nila Josh nga amo na lang nang gamiton kay para mas simple. Pero if you're going to read McCabe, you tried reading McCabe, and for the rest who are reading McCabe, si McCabe galing gahatag gid value sang alpha. Sang taga component ay tagaan niya gid kaya alpha for the low boiling point component and high boiling point component para hindi kaya mag-assume nga isa la ang alpha sa ila. Then i-multiply mo giniya sa iya nga mole fraction sa kung sa feed man sa sini nga formula o kung sa distillate. But the problem give you the alpha. Amo na gani hamba ko nga kung hindi siya pag-ihatag sang problem ang alpha, just like in the case of John Couples, kung hindi paghatag ang alpha nga ikaw pamangita, kay very tedious gid magamit sang sining set sang formula nga mahalin ka sa step 1 pakadto di. Kay pagpangita pa lang nga daan sang alpha kinahanglan mo temperatures para sa imo pure vapor pressure. Or you can use the alpha nga ginasuggest man ni Josh nga ato na lang ang Sapinsky's equation nga alpha. Pwede man. But in your case, ang akon lang man niya is kung specify ko for example ang procedure that you use the alpha from Finsky's equation in this equation, then that would simplify things for us. Ang ako lang sumong ginapamangkot is based on the steps that I have outlined here. If I'll be the one to specify the option that you will use that way uniform sa entire class ang procedure na i-apply, would you have any question on how, or do you still have any question as to how you go about finding the R minimum using the procedure here, or finding after the R minimum, finding the N minimum? Anyway, ang N minimum may sample problem na kamuya kung paano na siya pangitaon. So ako na lang pamangkot, clear man sa inyo ang steps nga already or may ara pa kamo sang i-clarify? Are there still points to clarify? Because these are dapat clear na siya before you get the quiz on Thursday, because you're going to use the graph on Thursday. So if I will specify that alpha to be used will be the alpha that you will be getting using Finch's equation, then everybody should know how to get the alpha using Finch's equation. And you will simply have to substitute in here. Or if I will specify that you don't use this one, but rather use the crude way of finding, then that's it. You just find the crude. You just use the crude way of finding the x prime and the y prime. That is the case. Pero ang sa board exam niya, if you're going to ask me, gaagi, amo gini siyang gamiton niyo. And the alpha should be really provided. If it's not provided, then you can go to the alpha that Finsky suggests. Of course, the answer, hopefully, the answer will be found among the choices provided. Wala ka naman sa may magamit kung hindi siya nimo pag i-Finsky's equation. Kaya mabudlayan ka mangita sang temperature kung ang equilibrium, boiling point equilibrium diagram not provided. Kay dira mo malang na makuha ang temperatures sang bottom kag top sang tower. Ang feed temperature pwede gid ya magamit kay ini siya mo siyang pinaka crude man. Base mo na lang gid sa feed temperature, hindi ka mag-base sa temperature sang bottom's liquid kag distillate. So no more question here in determining the RM. That way you can find the N minimum na lang and get the theoretical number of stages. Everybody gets it?
No, miss, may sample solution kada miss ang amo na, miss.
Sang sini?
Oo, miss.
Ay, wala ako nag-prepare. Josh, kaya nakita ko may ara. Gidya sa kay Jan Kuplis kag kay McCabe. You go to Jan Kuplis and McCabe, I saw that there's a sample problem that you can read as to the application of this particular formula. So you read your McCabe and your Jan Kuplis. Kay koron kung ma-discuss ko sang isa pagig ka example, amo man to siya gyapon nga procedure akong sundon. So better read na lang the sample problems because I thought wala gid sa sample problem that will utilize this equation. Nakita ko may ara and naka-trial and error gid siya. So makita niyo kung paano ya gin use ang trial and error magpangita sang alpha that will be appropriate in this portion in here. So I suggest you read that part. That way, ang ato na lang i-discuss ya ang mga part hindi trial and error nga makadiretso kita ya solve na, hindi ta mag-trial and error. So no more question in here. Read your, specifically, I gave you items in McCabe to read. That's 22 point, if I'm not mistaken, I have my McCabe here. I gave you 22. Wait. I wrote it here. Wait lang. In your reading assignments, I put 21.3. Let me just check. If you read the sample problems, you are okay. 21.3 and 21.4 in McCabe. As for Janku, please, I said you read example 11.6, that's 2. However, these examples does not illustrate the use of the trial and error procedure of finding the data. Specifically, the example that discusses the ways of finding the data in trial and error is 11.7-3 of Janku, please. In the case of McCabe, ara na siya sa multi-component distillation actually nga topic. Let me see. It's starting with 22.3, it allows you to solve the N minimum there. To 22-4. There you have the alpha and you have the corresponding F. Taga component gina-provided yung sang alpha. Kay budlay nga kamo ang mangita sang alpha. So kung ang problem hindi makatag sang alpha, then get the alpha using Finsky's equation. McCabe, if you're writing this down, ang McCabe nga example that discusses the use of the trial and error procedure is example 22.4, page 751 of the 7th edition of McCabe. It's a 4-component distillation problem. And in the case of John Couples, it's 11.7-3. 11.7-3, page 750. It uses the formula wherein you are to find the theta before you can find the R minimum. Galing kay kung mag-graphical naman ta sa quiz na nagamit yun na sa previous tanga discussion ng graphical eh. So I want you to really use the equations that I'm giving you now. Kay kung makuha man lang ang n minimum ninyo nga simple sa graph, hindi na kamo mag-solve using Finch's equation. But the thing is, you're still determining the alpha. So you have to determine gidya the alpha. Or you need still know how to solve for the alpha. So it's important that you really understand these steps that I have placed in here. I have inserted it in here and the assignment also on the last page. That is why I've edited the slide. That way it will agree with the one that I have posted in Canvas. So the main goal of the quiz, since it's analytical, is for you to be able to use this correlation and the equivalent in pairs. So this is our goal. You need not worry about the alpha because I will be providing the alpha if the system is not benzene toluene, because I don't see in the book boiling point equilibrium diagram for other systems. It's just benzene and toluene that I have seen, unless I haven't seen the other editions that may have for other systems. For iyalan na per mini benzene and toluene. So if your system is not benzene and toluene, I'll be the one to specify what would be the basis of determining alpha. So ang importante lang is how you know how to find alpha given the basis that you will use in finding it. That way, your answers will all be uniform. So if I say you find alpha based on the feed temperature, then base it on the feed temperature. The thing is, if you're going to base it on the feed temperature, the problem should also give you the feed temperature. If it's going to be based on the average temperature of the top and the bottom of the tower, that would be based upon the mole fractions of the bottom's liquid and the distillate. And that would need the boiling point equilibrium diagram that I have mentioned. If there's no way for other systems that could be known, then I'll be providing with you with the alpha. That is the case. Do you have any more questions here? Okay. If you notice, unit operations is more on steps. So it's important that you need to follow the steps, or you understand how the steps are to be followed. So that is why I keep on asking, do you have any question here? So if you don't have any question, then I assume that it's clear to you. Then I'd like to go to the next topic, which is extraction. Let me check. Okay, so this is the last topic for midterm, liquid-liquid extraction. I will just be discussing the intro for this afternoon. The rest of the problem solving that we will be doing with liquid-liquid extraction, basically concentrating on the design of the column, the extraction column. We will be discussing on the next week, because Wednesday I give that to you to prepare for your quiz on Thursday. Okay, so that would be a synchronous way of studying for your quiz on Thursday. Now, when you speak of liquid-liquid extraction, so these are the manner in which we define liquid-liquid extraction. So it's a process of separating the components of a liquid, and that is the feed, by contact with a second liquid phase, the solvent, with the two phases being chemically different. So the two phases that are contacted are chemically different. Another way of defining it would be it's the transfer of components from one phase to the other, which is driven by a deviation from thermodynamic equilibrium. The phases that we're talking about here are all liquid phases. Now, it's also a separation in which the difference in physical and chemical properties, such as differences in polarity and the water-loving or water-hating character of the solvent, is being capitalized on. So a separation according to the difference in physical and chemical properties. And these are just examples. So difference in polarity or the hydrophobic and hydrophilic character of the components in the feed and that of the solvent. Now, in the process of extraction, we're producing two liquid phases. So with the two liquid phases contacted, we are also producing two liquid phases. One is called the extract and the other one is called the raffinate. The component of interest is in the extract. So that's the component that carries with it the component. This is the rather the phase, the produced phase that carries with it the component from the feed that needs to be separated from the other components. This is the main, shall I say, this is the main product stream, and this is the byproduct stream, the raffinate. Okay, most of the unwanted components are in the raffinate. Now, as to specific applications, sometimes liquid-liquid extraction is being used as an alternative of distillation. Although the thing with liquid-liquid extraction is sometimes distillation is highly favored over it because this one uses a solvent. So if this one uses a solvent, there is a need for the solvent to be separated from the component that it extracted from the feed. That way it can be reused. And the process of separating the solvent from the component of interest that it extracted from the feed also entails, again, expense. So that is why distillation is preferred, highly preferred than extraction. But there are processes that really requires extraction, such as the one that I'm going to mention here. So one is if we want to remove acetic acid from water. So in this case, an organic solvent is being used. Although distillation can also, in this case, be used. So this is a case of removing the acetic acid, which is a contaminant in your water, living pure water. Now, another one is in the recovery of high molecular weight fatty acids from vegetable oil. This time, your solvent is specified already as propane, so it's also organic. Now, another option is high vacuum distillation. Now, this is the one that I have mentioned that though liquid-liquid extraction entails expense in the use of the solvent, and in the reuse of the said solvent, we need several physical steps to follow after extraction to separate it from the component it took out from the feed. If you're going to use distillation, the only one that can accomplish this one is high vacuum distillation. If it's high vacuum distillation, this will also be another added expense, because high vacuum distillation is also another intensive process. It uses a lot of energy. So they'd rather go for the use of propane as the solvent that will extract these fatty acids from vegetable oil rather than using distillation. Now, in the first one, you are removing a contaminant, and in here you are recovering the desired component, which is the fatty acid. Now, we can also have the separation of penicillin from the fermentation broth or mixture. So this is the recovery of a desired component. In this case, that would be penicillin. Now, in the case of the mining industry, we have metal separation of aqueous solutions of copper iron or uranium vanadium and tantalum columbium. So we need to separate metals which are considered contaminants to metals of interest that is being mined. So in this process, in this particular case, we're using liquid-liquid extraction to do that particular process of separation. Now, there are two main classes of solvent extraction equipment. So it could be a simple vessel with an agitation system to homogenize the mixture, and then later on allow the extract to be removed as the upper stream and the raffinate as the lower stream. Now, or it could be vessels in which mixing is done by the flow of fluids themselves. So there could be some form of mechanical agitation, or the mixing in this case, in the second bullet here, is through the means of the flow of the fluids themselves. So the flow must be turbulent. That way, the fluids themselves are already mixed in the process. Now, when we speak of the feed in extraction, it is composed of what we call the feed solvent or the carrier solvent and the solute. Now, how do you know that this particular component is the solute and all the rest of the components are your feed solvent? It's because your solute is the minor component in the solution. The feed solvent or the carrier solvent is the major liquid component in your feed. So the feed is the solution that contains the components to be separated. So it's the one that is being processed. The one that is used to extract the component from the feed is the solvent, the extraction solvent. Now, there are other terms here which we will be discussing next meeting. So in relation to liquid-liquid extraction, and it's very important that you know these terms. I will upload this uh, slide in Canvas as well later on. So please read on this. These terms can be read only from Perry's handbook. As if I can recall, I don't see these particular terms being discussed in detail in McCabe or in John Copley. So please, if I have already made this available for you, please read through the slides. And should you still have any clarification regarding distillation, especially the latter portion, feel free to message me privately using Facebook. Don't message me to the email because it will just probably be piled one on top of the other of the things that I need to do also uh, based on directives from admin, which uses my email as the way of communicating to us. So just place it on our GC, or you can privately message me through Facebook. Okay, so I will stop from here, and message me should you have anything to ask or clarify. If there's none, then good. But if you have anything to clarify, don't hesitate to message me. Okay? So that's it for this afternoon class. Bye for now. And thank you for listening.
Thank you, Miss.
Okay, thank you. Thank you.